In the next few slides, we are going to study the Laplace transform of the signal e minus at multiplied by the Heaviside function ut. What does e minus at look like? Let's take a look at this figure. In this figure, we have e minus at, the signal, multiplied by ut. Ut is the Heaviside function. The Heaviside function looks like this. At time 0, it will make a step up, unit step 1, and before time 0, it has value 0. So this green line is the Heaviside function. Now, what it does is that it converts any signal into a causal signal. That means the signal only exists on the right hand side of time. So e minus at times ut looks like this. What about the value of a? In this example, a is a positive value because it is obvious now. For example, e minus 1t, as t goes bigger and bigger, will be e minus a negative value, become smaller and smaller. So that is why this is a exponential that is decaying with respect to time. So this is e minus at ut, and this is the first signal that we will try to find the Laplace transform of. Typically, if you are an engineer, you go to a lookup table, and on the left hand side you have the function in time. You'll find the signal you are interested in. Now the signal just says e minus at, didn't write ut, but typically if this table says that I am a unilateral transform, then what he's assuming is that the signal only exists on the right hand side of time. So e minus at on the left, and then on the right hand side is the corresponding Laplace transform pair of the signal, and here it shows that this is the Laplace transform of e minus at ut. Right, let's remind ourselves what is S again. S is the complex number. So the Laplace transform of a function in time gives you a function in a complex function. By substituting different s here, you will get f of s as a complex surface. Okay, now we can plot the complex surface typically in the log scale or the magnitude scale, so you must be careful here. So if you say this is my s, or this is my s, the entire s, which is the complex number, and then now you have to plot the magnitude, so you get here the magnitude of f of s, and you can, for every point, you can plot some magnitude and you'll get a surface. Alright, then if you only get the magnitude, what about the phase? Of course, then you have to create another figure here, and this is also the same s, and then you can plot the angle here at different position of s. So you can plot the magnitude and the phase. Alright, let's try to do one of these Laplace transform by hand. Okay, so we are going to perform the Laplace transform of the exponential function e minus at ut. So we are interested in the unilateral transform. Well, we know that because, see, we are only integrating with respect to the positive time. Let's put our signal here, e minus at, which is our f of t, integrating from 0 to infinity, and we multiply by e minus st dt. We'll use the law of exponent to collect e minus st and e minus at together, and there we have it. Now all we are doing is the integration of, let's say, e to the power of kt dt, and we know that this is equals to 1 over k e kt from the what do you call it, the limit a to b. Alright, that's all we are doing. So if you plug in this formula, minus brackets s plus a drops out here, and on top is the original function itself. This is the limit of integration. Now we plug in the limit of integration. We have an infinity here and we have a 0 here. We are putting this value as t equals to 0 and infinity. So t equals to 0 is 1 and t equals to infinity is here. Now, something interesting happens when t equals to infinity. When s plus a is greater than 0. When s plus a is greater than 0, e minus some positive number times infinity is a very negative number, and this is 0. So we like that to happen, because when that happens, then our f of s will converge. If e minus, let's say this is a negative number, infinity, then this is e positive number, infinity, then what happened? Then this tends to infinity. So the equation does not converge. So what we are saying in this example is that we definitely want s to be greater, s plus a to be greater than 0, implying s must be greater than a. Okay, that's the region of convergence, or actually the real part of s needs to be greater than a. Now, we are finished with this. We have done a simple example of Laplace transform of an decaying exponential, and we are saying that s plus a must be greater than 0. Let's plot the Laplace transform of e minus 1t. This is 1 over s plus 1. So e minus 1t is the function in time, and this is f of s. Okay, we are just using a fixed value of a here. A is 1, implying s must be greater than minus 1. So for it to converge, s, the surface, the real part of s must be greater than minus 1. So I'm going to draw where is s. This is the entire s plane. This is the real axis here. So this is 0, this is 1, this is 2, this is minus 1, and this is minus 2 along the real axis. Here is the imaginary axis. This is 0, this is j1, and this is j2. This is minus j1, and this is minus j2. Alright. We say that the s value must be greater than minus 1. So I draw a green line for you here to show you exactly where is s equals to minus 1. This green line here. When s is greater than minus 1, what we are saying is that all this region here. I also plotted the corresponding line of what do you call that? The green line on the surface. And what we are saying is that only surface on the right hand side, s greater than minus 1, exists. So I'm now going to draw for you where it exists. So this surface is okay. What about the surface on the left? Let's use the red. This surface, although we can plot it because it is just 1 over s plus a, this surface does not exist. This surface does not represent the Laplace transform of the e minus 1t. So in fact, the second figure will show you exactly like I actually chopped the figure and removed the red part. So this figure is the Laplace transform of e minus 1t. Right. Now, where's the interesting part in the surface is the peak, of course. Where is this peak? Well, this peak exists when s equals to minus 1, because why? This is equals to 1 over s plus a. What happened when s equals to minus 1? When you substitute s equals to minus 1, is 1 over minus 1, and a, remember, is 1. So minus 1 plus 1 will give you 0, and therefore the whole thing goes to infinity. That's why this infinity occurs. Where is s equals to -1 is here. -1, j is 0. So it's exactly at this point along the real line. S equals to -1, and we put a star there, or a pole there, or cross there to tell you that at this point the function goes to infinity. Okay. Right. Sometimes if you are really lazy, instead of drawing the real figure, we draw it in 2 dimensions. So now, how do we interpret this diagram? Is we are plotting the surface here, where the red is, as here. And we are saying that everything on the right hand side of s equals to -1 has the region of convergence. It is a valid Laplace transform. We are just saying that this region is the region that has the region of convergence, that it exists. What about those on the left hand side? And the left hand side, now I will draw it in orange. These guys do not exist. Okay, and the star here, that pole here position, is again the most important one. It will characterize the function in the S domain. Will show you exactly where it is. It is s equals to -1 plus j0 if you are really interested in knowing that the imaginary part is 0. Okay, so this is the first example. We went from a time domain into the S domain, and we see the figure. Alright, thank you.